I'm going to talk a little bit about some history we have in climate and climate change assessments. And I'm probably going to be talking more about problems than solutions here, but maybe there's some enterprising graduate students in the audience who will figure out what the solutions are. So I guess if I advance this. So on my shelf is a dusty copy of an Academy report dated 1977. The lead author was the late Jim Wallace. There's about 14 authors or so on that. I recognize the names of about half of them, and none of them, unfortunately, are still alive. This report came out 2 years after I finished my PhD dissertation. When I looked over the report again, and it survived the move from UW down to UCLA about 10 years ago, many reports did not, went to recycling. I leafed through it, and the one thing that was obvious is this report was written by what I would characterize as a team of rivals, if any of you have read the book about Abraham Lincoln. But in amongst, and it was written not long after the major concern was not temperature increases, but temperature decreases, given the records of the previous 40 years or so at that point. But there was a notation in there, or a brief paragraph in the overview that Jim Wallace wrote, noting that with the amount of CO2 that had been emitted into the atmosphere since the Industrial Revolution, it accounted for maybe 2 or 3/10 of a degree C of warming over global land. And looking forward, this may well be a problem. In 1982, one of the first papers looking at water resources implications of climate change was written by Nemec and Shockey in Hydrologic Sciences Journal. And I'm going to go, there's a few of these papers, and I'm just going to give the very briefest of encapsulation. They did some sensitivity analysis to precipitation changes and potential evapotranspiration changes in 2 watersheds, one in Texas, one I think in Mississippi. They used something called the Sacramento watershed model, which was relatively new at that point. Believe it or not, that is most of the U.S. river forecast centers continue to use that model for flood forecasting. It was a spatially lumped model, and they did sensitivity analyses. They simply changed the precipitation, changed the potential evapotranspiration, and they look at sensitivity of the mean runoff in those particular river basins. Going forward later in that decade, Peter Glick in his dissertation looked at the Sacramento River Basin. There's actually a companion paper in which this is a model description paper. He also used the Sacramento model, applied to the Sacramento and San Joaquin River basins. And in a companion paper in climatic change, they looked at output from, I think, 3 general circulation models, one of the first times this was actually done. They simply took averages, and there were some scenarios in terms of global emissions, and they rescaled observed precipitation and temperature, and they did some analysis. And not surprisingly, what they found was wwarmer temperatures, snowpack melted earlier, and there was major shifts in the seasonal hydrograph. Somewhat later on in that decade, actually, the paper came out in 1990, there was something called the EPA Reports to Congress. They were asked to go document what might happen due to climate change across the U.S. And it was a matrix design where they had different sectors, of which water was one, and they had different regions. California was one. I got a phone call sometime in the mid-1980s from Pete Hawkins, who was then at Utah State University, saying they were doing this study and they needed somebody to go model the hydrology of California and how climate change might impact it. And what I told Pete is I said, well, we might be able to do a sample watershed, and we might be able to put a hypothetical reservoir with it to look and see what might happen with reliability. And Pete said, well, that's not going to do it. They want to do all of California, which we had no clue how to do, to be perfectly honest. But I needed the money, so I said, we'll figure something out. And the something we figured out was pretty much glommed together and is in that 1990 WRR paper. We also used the Sacramento model because we knew how to use it. We used 4 index watersheds, and then we did something with a stochastic model to link them together and get flows for the entire Sacramento and San Joaquin system, which a companion paper, Dan Shear, did the work on, ran a reservoir model to look at reliability. To my knowledge, this is one of the first times this was actually done. We took the GCMs and we just took changes in the GCMs between, and then it was CO2 doubling what everybody was using, and the current climate, and rescaled the precipitation and the temperature. So fast forward a little bit, well, okay, so this is a schematic that kind of comes out of a paper by Julie Vano about 10 years ago. And all of that spider web is starting with a global model, which is where the climate projections are coming from, for better or worse, trying to get down to stream flow. And one could also imagine another oval down at the bottom, which would be a water management model. What does it actually mean for reliability? And the key in this particular visual, I guess I can't really get to that. There's a pathway here called downscaling to get from the GCM down to the hydrology model, and there's a pathway that goes through a regional model. Those 2 pathways have been the source of much discussion over the years. The physically based way to do it is to run a regional climate model. However, until very recently, it hasn't been really feasible to do that for very many scenarios, and what people have reverted to, including ourselves and almost all of our work until recently, has been statistical downscaling, and that is a whole industry of itself. So one of the first times we did this was for the Upper Colorado River Basin, work by Nicholas Christensen, in a paper that I think is early 2000s, 2004 or something like that. There we used 11 different GCMs and I think a couple of different emission scenarios, and Nicholas also had put together a very simple reservoir model so we could go look at what was the effect of projected climate change. Turns out the Colorado River Basin is very interesting because unlike most river basins, the reservoirs are very large relative to the mean annual flow, and the management issues are mostly about annual flows and total volumes and not so much seasonal changes. So the seasonal changes associated with warming aren't the big issue. The changes in volume are, and those haven't been very well understood in the Colorado until fairly recently, in particular 2020, what I consider a seminal paper by Chris Milley that has tracked down that what's really going on there has to do with temperatures, changes in snowpack, changes in albedo and net radiation driving more evapotranspiration. And as a sort of humorous aside, I made a comment in Chris Milley's retirement symposium about, he could have titled the paper, "It's the Radiation, Stupid." And Chris didn't really take that. He made a comment to the effect, you know, we spent a lot of time thinking about the title of that paper. It is the radiation. The title is much more informative. In any event, we use like 11 GCMs, I think, run through statistical downscaling in our work there. We did a study of Western U.S., which this was done when just before I left UW, and I can't remember how many GCMs were used. The one thing that I want to point out is in this sort of whole evolving, what I call industry of climate change and water assessments, periodically, and most of you I'm sure are aware of this, the IPCC reports come along every, 5, 6, 7 years. All these global centers that are doing the climate modeling run their newest, greatest model, and those all get archived somewhere. They kind of dribble in and then they get analyzed. So one of the interesting issues that arises is, and for water managers, everything kind of changes every 5 years. What do they do with their planning? The best example of that is between CMIP 3 and CMIP 5 in the Colorado River Basin. The precipitation scenarios and the changes in precipitation reduced quite a bit in CMIP 5 relative to CMIP 3. And there had been a lot of concern, obviously, for declining flows in the Colorado. What differences make? It turns out the upper of those two plots is actually temperatures between the two, and the distributions across the GCMs wasn't that much different, but there was clear separation. That whole issue resulted in a paper by Brad Udall and Jonathan Overpeck, and what it really has to do is arguing that, look, there's a lot of uncertainty in the precipitation, as witnessed the CMIP 3, CMIP 5 business, but the real issue here is temperature and the sensitivity to temperature. And people have started talking about, and the Milley et al. Paper gets into this in detail, the physics behind it, the sensitivity in percent flow change per degree C. There's more this whole industry of downscaling. Interestingly, the different methods, MACA, BCSD, LOCA more recently, they're all 4-letter acronyms. Not going to go into the details. It does make a difference how you do that. That's really what that paper was about. And some other issues with sensitivity here in how you actually do the downscaling. Now, more recently, we've started working with people in our Atmosphere and Ocean Sciences Department at UCLA on dynamically downscaled using WRF, which is more or less the standard in the industry, weather research and forecast model, and begin to have some success in reproducing distributions of stream flow, and I don't show it here, but also snowpack over the California watersheds. This has been something that we've been looking to for a long time, and the ability to do multiple GCMs is now more or less there. However, one of the things I want to leave you with is this whole enterprise of producing all of these scenarios. You fill terabytes of disk, and you make mistakes, to be perfectly honest. I won't have time to get into the details here because I'm out of time, but even in this most recent stuff over California, we found some glitches. It's easy enough to happen. There's a lot of moving parts, lots of output. This issue that it all gets iterated, everything gets done again every 5 to 7 years. Statistical downscaling has shortcomings. Until recently, dynamic downscaling has been computationally prohibitive. It looks like we may be more or less past that. Alternatives, just leave you with this. There's a couple, I think Casey Brown may be on the program later. I thought I saw his name, no? I guess you got a video from him. Casey has some work on what he calls bottom-up rather than top-down. What I've talked about is top-down, going through all the downscaling, producing the terabytes of data. His idea is look at more at the pressure points of how the system operates and see what is controlling that. There's also some work that Julie Vano did in sort of shortcutting some of the production of all this stuff by using sensitivities, and you can at least get sort of interim results without going through the whole process. But we still have a little bit of an issue, and you know, when we talk about, okay, what are the issues globally with water and so on, climate clearly comes up. You're going to be asked the question of how are climate change projections factoring into this, and how do you do that? And that's where this enterprise sort of fits in, and exactly how to do this, and are we going to keep doing these things every 5 to 7 years over and over again, or is there a better way? And that's where I leave you with the problem and not the solution. Thanks.
So I was going to throw one at you. You were also part of a paper called Stationarity is Dead. Well, it wasn't ever there, right? So, but you know, Dennis, a lot of your earlier work was actually related to systems performance and hydrological measures that would go in that direction. What I've seen with much of the downscaling activities and so on is that they don't seem to acknowledge that that is one of the goals of water management. And so the fact that there is interannual decadal variability that none of the models get right, that doesn't get downscaled, et cetera, is missed. So what we are at is exactly what you pointed out, is the big focus is responding to the climate scientist question of if there is warming, what's the sensitivity of precipitation and what's the sensitivity of stream flow to it? Do you have some thoughts on whether we are actually even on the right problem or not?
Well, okay, so if you go back way earlier in my career, and you were part of this and around when all the Hearst effect stuff was in, for those of people who aren't familiar with that, a lot of emphasis in the 1970s was on long-term behavior of geophysical records and stream flow in particular, and the low-frequency behavior, which it was shown the interannual variability has typical persistences which last longer than sort of a year or two. And there's some famous work done on the Nile River by Hearst, and that's who the whole thing is named for. So along came sort of climate change, and the difference as I characterize it, and there's been some tension in the hydrologic community, comment papers on the stationarity is dead and so on. The one argument is that, well, you know, it's really all about long-term persistence. But what I characterize it as is that if you've got long-term persistence, if you wait long enough, it'll come back, okay? Whereas if you have fundamental changes in the physics of the atmosphere, it's not going to come back. So it's not really the same thing. Nonetheless, there are questions as to whether the climate models adequately characterize the long-term persistence. I'm trying to remember the fellow's name in the Netherlands. I reviewed a paper of his 15 years ago probably, and it didn't get published, it got killed. I think because the climate community didn't like it, but it was comparing Hearst effect out of GCM simulations and out of observations, and they didn't match. The GCMs have much shorter term persistence. So I think there still is an issue there. Whether it's a practical one or a theoretical one, I don't know.
I think what it gets to is the statistics of drought and the recurrence statistics, the duration statistics, those things don't work, right? So we have two problems. One is what happens on the average water availability, and the second is what happens to those drought statistics. And both, I think they're not the same problem, is the point.
Well, so we could get into a much longer discussion also where I get myself in trouble with the climate community, but some of these statistics, and the ones that really matter to us, are floods and droughts, right?
Exactly.
I think you mentioned that before. We have a bit of a mismatch between what the climate models say and what we got out of observations. I'm sure, you know, the Justin Sheffield paper from when, 2010 or so, he didn't make himself very popular. The title of the paper was No Evidence of Long-Term Shifts in Droughts. Across the U.S., we found basically the same thing, that the major droughts are mostly early in the record. In fact, I think there's one paper I wrote with Kingsley Moe where of 15 major droughts we classified over the 100 years of record across the conterminous U.S., only 2 of them were post-1980. I think it was 1988 and maybe 2012. All the others were first half of the record. A lot of it was 30s and 50s. Okay, so there's still some open questions. And with floods, same thing. There's a literature out there. It's hard to find. You can find evidence that precipitation extremes are increasing. Much harder to find it in the flood records. What you do find is the damages are going up, but that's because of development on the floodplain.
Yeah. Okay. Nobody sent questions in, so okay. Well, let's thank Dennis and. Oh, there is one. Okay. Oh, there you are.
I was just curious, kind of as a follow-up to that question.
I may need amplification. Sorry, my hearing isn't what it used to be.
So just as a follow-up to that question, I was curious if you could comment on what do you think are the time horizons that we as hydrologists should be providing information over, that people actually can use that information? So we're kind of driven by the IPCC projections and we run things out as long as they provide, but what are the timescales that we should actually be providing estimates of risk over?
Well, economically, 40 years is the answer, right? I think that's what it always used to be. But now the tension becomes whether you should be doing economics, if you have issues with irreversible change, you know, the infrastructure's around for longer than that. So, you know, what we find in doing these climate change assessments is the 40 years is a flippant answer. But mostly what the water management agents, they don't want to see the 2099 stuff so much. They want kind of 40 to 50 years. Now, whether that's the right perspective or not, I don't know. Okay.
Thanks.
Do you want this back? Or?